Any questions for me, you just have to message me in the chat. Publicly or privately is okay, and I'll get to you as quickly as I can. Today's guest is Dr. Ali Hadigheh, and he'll be presenting on sustainable materials and all that. Sorry. Currently, Ali's research advances our understanding of how sustainable, resilient, and green engineering materials function in structural applications. So his research expertise is in the recycling of fiber-reinforced polymer composites and industrial byproducts and material and performance-based characterization, structural health monitoring, and development of multifunctional composites for smart structures via experimental advanced computational modeling and machine learning techniques. Now, I know that sounds like a lot, but I'm sure that Dr. Ali will be able to explain it in a much better way than I can. So without further ado, Dr. Ali, please take it away.
Thanks, Pirovid. Thanks for this nice presentation. So I just try to share my screen. 1 and 2. So can you please confirm if you are seeing the slideshow?
Yes. Yes,
awesome. Thanks. Great. So good afternoon, everyone. Thanks for inviting me to this event to discuss about resilience and sustainability of infrastructure, and also our recent achievements at in our research group at UC in this area. So as Pirovid mentioned, my name is Ali Hadigheh, and I'm a senior lecturer in the School of Civil Engineering. Some of you might have some subjects with me, but mostly I teach CIVL 5277, structural rehabilitation and timber design. So before we begin the proceedings, I would like to acknowledge and pay respect to traditional owners of the land on which we meet, the Gadigal people of the Eora Nation. My presentation has you can see the outline of my presentation. I start with sustainability and the concept of sustainability and challenges that we have, and then I don't know if that is annotated here. Yes. Perfect. Okay, yeah, so then I introduce our research group, Smart Materials and Sustainable Structures group in our school. And then I thought probably this session would be much better we not talk about the theory, mostly about the industry applications of our research. So I mainly talk about 2 recent projects that we are doing with industry related to sustainability and recycling of materials. So the first one is about cathodic protection systems that we do with Transport for New South Wales, and the other one is about recycling of fiber reinforced polymer composites. So the UN Sustainable Development Goals, which you probably have heard of, and I'm pretty sure you know about that, they are an urgent call for action by all countries in a global partnership. They are mainly focusing on adaptation, finance, mitigation, and collaboration to reduce coal and scaling up clean power, clean energy, and protect our resources and habitats, accelerate the transition to clean energy and transition to net zero. So as part of that, it also recognizes the role of innovation and technology in reaching these climate change goals. Mission innovation strategically emphasizes on carbon dioxide removal using advanced technologies or urban transition to provide a pathway for cities to adapt net zero carbon solutions, and also net zero industries for unlocking emissions at heavy industries such as steel, cement production, and integrated biorefineries for replacing biofuels. So amongst these resilient and sustainable built environment plays a key role to achieve the net zero emission target. This is it is estimated around 40% of global energy-related greenhouse gas emission is produced by built environments. So to achieve a goal for this net zero emission by 2050, direct building CO2 emissions need to decrease by roughly around 50%, and indirect building sector emission must drop by around 60% in power generation emissions. So these highlight the importance and key role of sustainable and resilient infrastructures in achieving net zero target. So to address these challenges, in my research group, we focus on multidisciplinary teams to develop and implement innovative materials and systems in order to provide sustainable and more durable and less resource-intensive infrastructure. Our research mainly focus on understanding of how sustainable, resilient, and green engineering materials function in structural applications. So you can see some of my PhD students and my research team. We also have a group of a couple of undergraduate research students. We also, as part of these projects, we mainly within my group, we work collaboratively with various industries, including Australian Research Council, different state government sectors, and also local councils and private sectors. So, for example, one of the projects that I am talking here is about development of sustainable mortars for cathodic protection of critical infrastructure such as reinforced concrete bridges in marine environment. So due to climate change, structures are being affected by increasingly larger scale and devastating natural disasters, which cost many lives as well as billions of dollars. So also a large number of our existing structures, as you know, don't satisfy the requirements of contemporary design standards. So they have been built many years ago and they are not complying current standards. So during an emergency, they may be vulnerable to structural or non-structural damages, and thus this can cause loss of functionality. Most of the structures built in also coastal areas. Amongst these, reinforced concrete structures are particularly susceptible to steel corrosion. These steel corrosions can happen due to carbonation, chloride diffusion, and acid attack. Based on climate change and temperature variation and increase in loading in traffic loads, these aggressive agents are more prominent and affecting the structures synergistically. So there is an estimate that maintaining bridges cost Australian taxpayers around $8 billion. So you can see the urgency of maintaining and rehabilitating these kind of infrastructure. So as part of this project, Impress Catholic, we developed innovative materials for Impress current cathodic protection systems, or briefly we call them ICCP systems. They are effective and widely used for corrosion protection of RC structures, which are mainly located in harsh marine environments. So what does that ICCP do and what that is? Basically, as part of this ICCP system, permanent anodes are embedded in concrete, and then they are covered by a kind of cementitious matrix overlay. And then they impress external DC current between these electrodes. And this results in a steel to become cathodic. So when a steel area becomes cathodic, then this ICCP system extracts the chloride away from the reinforcement bar toward the anode. And this increases the alkalinity level around the steel bar. So therefore, it generates kind of protective passive oxide layer around steel. So that's how that is designed to protect our steel reinforcement from further corrosion. So ICCP system is generally considered as the best available cathodic protection methods, but they have drawbacks, and they are very expensive to install and also very expensive to maintain. If you look at the cost of these, for example, for transport for New South Wales, we have around 40 bridges across New South Wales with these ICCP systems. And depending on the size of the bridge and the environment that bridge is located in, each bridge may cost from 1 million to 10 million, the installation and maintenance of these ICCP systems. So the challenge is that these ICCP systems based on a standard should service for about 50 years, but Transport for New South Wales has observed that they need to replace these systems after around 10 to 15 years. That's because of the acidification of that cementitious matrix that you can see here. So that is that acidification affect that matrix, and then that matrix is washed away from the surface. So that can damage the whole ICCP system, and that would be wouldn't be as effective as before. So this project, what we did, we looked at different options and looked at how we can improve acid resistance of these cementitious matrices. And we know that, considering that manufacturing of Portland cements accounts for about 7% of carbon dioxide emission globally. So any attempt that we can reduce the amount of cement in concrete would be really useful for us. So we looked around and we realized we can use industrial byproduct waste, for example, like fly ash, slag, silica fuel, rice husk ash. These kind of byproducts which are produced during the power generation or steel manufacturing, we can use these and incorporate into concrete and replace cement. On one hand, we reduce the amount of cement production. On the other hand, we also try to increase the acid resistance of these cementitious matrices. So we did investigate these materials, and we made samples, we tested these geopolymer concrete within various environments, obviously under different types of acidic environment, including hydrochloric acid. So that salt water in marine environment, they have, when we have ICCP, that reaction between this ICCP system and salt water creates hydrochloric acid, HCl. So in that environment, that degrades the bond between different parts of concrete, and that loses the concrete and washed away. So that's why we tested HCl on these concrete samples, and we tested them during the time, we casted them, tested them, and then we looked at properties of these samples in terms of mechanical properties, such as compressive strength test, tensile strength, shear, slant shear test. So you can see a couple of these results. For example, mass loss of samples within these acids. So if you look at these images, you can see from far left, we have control samples, but then toward the right, you can see we have samples which are exposed to acidic environment. So, but the interesting thing during these tests, we found that, for example, if you have harsher acid or a stronger acid, it doesn't necessarily mean that your structure would degrade quicker. For example, in this case, 32% HCl, the performance was much better than 10% HCl. So these are the aspects that we did the test on, and we realized these are need to be considered when we do design and when we do construction. So we also looked at the material characterization tests, such as SEM. And by looking at these SEM, I think probably everyone knows what SEM is, a scanning electron microscopy. And you can look at samples in very small scale, micrometer scale, and look at how those tiny elements are interacting with each other, or if there is any crack happening within your concrete, and so on. So we did a SEM, and that showed a notable formation of the micro cracking and high surface roughness and porosity when we increased the level of acid exposure. So when we compared that with control samples, we realized control samples had much better homogeneous and flatter surface. So basically, these microcracks tended to initiate from the interface of aggregates, and then penetrated into that segregated debonded area, and then they made complete debonding and caused the total failure. So we also did X-ray diffraction analysis, and that showed that acid immersion had no major effect on the phase structure of geopolymer concrete. So we did all these tests within our lab, and then we showed that geopolymer concrete and this type of concrete, which is made of recycled materials, perform better than OPC in acidic environment in terms of material within material level. So to test this in practice, we applied this mortar onto a bridge in New South Wales region. And the bridge was originally built in 1920s and was refurbished in 1980s. The bridge was showing signs of deterioration during the time due to exposure to chloride, carbonation, and sulfate. Also, the good thing about this bridge was, as you can see in the image, it was rehabilitated by steel jacketing around one of the columns. So we tried to see if we apply this technique, how our mortar will perform and how our structure will perform within this environment. So we did, because we couldn't monitor it during a long period of time, so we did finite element analysis on that, and we used Abacus software, and we created exact model of the column, and then we applied our mortar, considering the diffusion coefficient of different types of materials. We could define how much of acid can penetrate into our concrete. So with our mortar, that showed that that can delay penetration of acid, and it can last longer than OPC concrete. So the other attempt that we did, so as you saw in the photo, we had a steel jacketing. We thought, let's see if we replace this steel jacketing with FRP materials, fiber reinforced polymer composites, what will happen and how that penetration will either deferred or that increase, or speed up. So as you can see here in these images, the profile that within the depth of the member in concrete member, concrete substrate, you can see that penetration and diffusion has been delayed dramatically. So that showed that this process can be easily used in also practice. So another, the other project that we also do, we did, which is sort of aligned with this project, is the work that my PhD student did on using machine learning techniques for durability assessment of FRP to concrete connections. K1, my PhD student, he developed, he actually compared different machine learning techniques and collected a large amount of data from literature and analyzed those data and developed machine learning techniques, and showed that you can see here on the bottom right corner of the slide that machine learning models can provide good representation of the performance, and they can predict the performance with high accuracy, specifically artificial neural network in this case. So he also looked at how these type of composite connections will perform if we change sustained load, or if we change the duration of loading, or the relative humidity of the environment, or temperature, or so on. So he could do the parametric study on these composites. So this was the project that we've done, and now I think the second project I want to show you guys is another interesting project that we are doing currently with a couple of my PhD students in our group. And we are focusing mainly on developing sustainable solutions for recycling of FRP end-of-life scraps and cutoffs to upcycle composite waste. So the project is funded by Australian Research Council, and we also collaborate within this project with various industry, such as Wagner in Toowoomba. They are active in making composite profiles for construction. Quick Step, which they make aircraft parts, and the other industries in this area. So to give you some background about these type of composite fiber reinforced polymer composites, or shortly FRPs, they get their strength from long, continuous, and precisely aligned fibers, which are fixed within a polymer matrix, like, for example, epoxy, and they are cured at ambient temperature or high temperature. To give you a better perspective, these you can see from these pictures, the diameter of these fibers, they are around 1/10 of human hair. So, but with this very small diameter, the strength is almost between 7 to 10 times more than steel. So you can see how strong these materials are, that these superior properties and these superior properties promoted this high usage growth rate, which we can see in aerospace, defense, construction, renewable energy, like, for example, turbine blades and so on, which is actually very useful for production of lightweight structures. So they have higher strength but low weight. So it is the perfect material for making the structures. But these high performance materials, they have a major drawback. They are wasteful to produce and difficult to recycle. When they are cured, usually FRP composites can simply be melted down and reformed or recycled. So as a result, most of waste produced they are disposed of in landfill or incinerated. So, for example, in Australia, all of these waste materials are sent to landfill. So none of these materials are recycled currently in Australia. So with this current production growth, these FRP materials will be one of the largest waste streams in Australia and around the world. So if sustainable methods are not developed to reuse and recycle composites, the potential hazards of these materials to the environment and human health and national economy, in my opinion, will be far greater than the projected hazards of plastic waste, because these materials are nanomaterials, and for example, manufacturer itself tells you they never degrade. So if they are sent to landfill, they stay there for centuries and centuries. So in the case of carbon fiber, for example, recycling of this carbon fiber can dramatically reduce greenhouse gas emission, because production of these carbon fiber, virgin carbon fiber, is energy intensive and very expensive. That's why we use these materials in specific applications, like, for example, aerospace or spaceships or these sort of high-tech applications. So currently, the reuse and recycling of these composites is very, very limited. In Australia, is zero, less than 5% globally. So this is due to partial deterioration of mechanical properties of fiber during recycling and disorientation of these recycled fibers during the recovery process. And also, there's a huge lack of computational models for precise determination of mechanical performance of recycled FRP materials. So, having said that, there are few methods for recycling of FRP composites. They all have advantages and disadvantages in which they should be considered when a recycling process is designed. So common methods are pyrolysis process and mechanical and repurposing process. So pyrolysis, if you are not familiar with that, is basically a thermochemical method to recover clean fiber from polymer composite waste within oxygen-free conditions. So basically, you heat up your samples, your composites within a nitrogen environment, for example, inert atmosphere, and then separate your fiber from your epoxy. Another method is a mechanical recycling, which includes kind of different types like grinding, shredding, and combing. So to make an informed decision, it is essential to first evaluate the environmental and financial viability of these recycling methods. So we performed life cycle analysis and cost benefit analysis on these recycling methods by considering also technology readiness level, TRL, of these techniques. My PhD student Yanning Wei, she did a great work in this area, and she submitted her PhD thesis two days ago, and that's basically her work. She did cost benefit analysis and life cycle analysis to define how viable these methods are, and also how much of CO2 each recycling method produce. So, because you need to consider, always talking about recycling is not just the aim. You have to also see what type of recycling is suitable and produces less CO2. So by comparing these cost and values for these recycling methods, we realized that pyrolysis possibly would be one of the most affordable techniques. So we used that technique, we focused on that, and we basically developed techniques to recycle these carbon fiber from these composites. So in our research, we looked at these challenges. We developed an integrated recycling method for the recovery of the carbon fiber from composite waste. And we look at how these can be guided by kinetic analysis. You probably learned some methods during your learning about chemistry, about these kinetic analysis and so on. So we optimize this pyrolysis process to recycle these composites. So the other aspect is we develop these recycling technique, but how can we reuse these materials? As you remember, I mentioned that virgin carbon fiber is really high quality material because it is continuous, that is precisely shaped and aligned into a specific direction, such as the image, that top left corner that you can see. But when we do reclaim fiber from composite, these fibers are short and they are fluffy. Just imagine a bunch of hair on the ground, on the floor, and they are all entangled and fluffy and into each other. So that's very difficult to separate them. Also, you can't expect much of performance from these kind of randomly distributed fibers from the sections made of these randomly distributed fibers. So to realign these fibers, these recycled fibers, into the direction that we want and get the most benefit out of that, we developed a technique, a hybrid fiber alignment method, or HFAM, to align these fibers into the direction that we want. So we have a patent for that. Unfortunately, I can't explain too much about this technique because that is under patent. So I can't explain too much about that in this session. So other PhD student, Z1 Wang, he did focus on reusing carbon fiber offcuts. The interesting thing about carbon fiber industry is that, for example, when they are making fuselage of airplanes or wings of airplanes or even turbine blades, there are a lot of waste materials and offcuts during production process. So around 1/3 of fiber is wasted during the production process. So to reuse these materials, Z1 focused on how he can align these fibers and reuse them in different scenarios to get the best performance. And he tested them, and they realized that although these waste materials can't achieve the high performance of the virgin carbon fiber, but recycled products can be used for applications that usually a steel or aluminum is used for. So if you imagine that, you can use a lot of, instead of using a steel material or aluminum, which are far more expensive than recycled carbon fiber. So you can replace them with these waste materials. So to end it, I show this image. I don't know if you know what these are. These are turbine blades, and they are sent to landfill, and they are dumped in landfill after the end of their service life. So the purpose of our research, we hope that we can avoid such kind of situations, and we can really truly have a circular economy around these new technologies. Thank you.
Thank you so much, Dr. Hadigheh. Personally, I've never thought about this in depth about sustainable recyclable materials before, so this was really quite interesting. Now, we are doing a Q&A session very soon, so I'm sending the link inside the chat, and if anyone wants to ask any questions, we'll put it there. But for now, Dr. Ali, can you answer me this question? What are your biggest concerns for environmental sustainability going forward? And more importantly, what can be done about it?
That's a good question, actually. As this photo shows, when we talk about renewable energy and green energy, we have to be very careful how that is achieved. and if that green technology causes further problem in the future or not. So I guess the focus should be on more circularity instead of just, for example, about the turbine blades or electric cars, the batteries. If all of cars move to become EVs, and then what will happen to the batteries and how we can provide those resources. So that circularity is very important, that new technology, new advanced materials don't cause further problem for the environment. So this should be considered when you design materials, when you design your parts. For example, instead of design for durability, or design for example, structural performance, you design for recycling, design your materials in a way that you know that material can be recycled in the future.
Well, that's quite interesting to think about it that way in the future. But from our perspective, you know, as young graduates or undergraduates, how much growing room is there for us in the environmental material and the smart building industry?
Yeah, I guess that's a good time for you guys specifically to get into this space, because as you see always in the news and everywhere, that there are talks about clean energy, clean environment, and recycling, these sort of things. So that is a great opportunity as young engineers to you may have better ideas how to do recycling, what kind of materials to use instead of the current materials that are carbon heavy and energy intensive. So I guess that's a great opportunity at the moment, which is supported by government and also different industries. If you look at most of major industries, they have branches that they look at how they can reduce their carbon emission. And the beauty about civil engineering and construction is that, as I said, 40% of our global emission is related somehow to built environment. So civil engineering and construction is one of the major subjects that's the expertise of civil engineers. So I guess that would be a really good opportunity for our students to get into that space.
All right, so I hope anyone who's looking to get into sustainable materials is paying attention, because this is very crucial information, if you ask me. Let me just share my screen real quick. All right, can everyone see that? Okay, so we're just doing a Q&A session. So will these be things that we'll be learning in our course? Seems to be the most burning question at the moment.
That's a very good question. I guess there are some sustainability subjects, sustainability related subjects that they are offered by different schools. I don't know particularly our school is offering that, but I know universities and also civil engineering faculty, they have subjects, they offer these sort of sustainability related units.
Okay. Another question here is, how are these ideas or techniques created or thought of?
For example, about the recycling, FRP recycling, the idea came to, for example, to my mind. I just talking about myself. It came to my mind in 2019 after working with composites within industry and academia as a researcher for almost 10-15 years. So then I thought, now so far I use these materials for strengthening of structures, or I used it in different various scenarios. But what will happen is there any recycling process made for these kind of materials or not? Because I was wondering, usually I remember when I was in industry, I went to a bridge, we were strengthening the bridge using these FRP composites, and a very small drop of the epoxy dropped on my glasses, and it remained there until I threw away that glass after 4 or 5 years later. So then I realized you can't, it's very difficult to get rid of these materials or recycle these. So then I thought, so what are the techniques that we can use? The interesting thing is that's also, I guess the benefit is to look at other industries, other disciplines, for example, in chemistry or in mechanical engineering or other type of discipline. What are the current methods, and maybe you can apply those methods into, for example, recycling of these composites. So these composites mainly used in aerospace and also in marine industries for many years, and we as civil engineers, we borrowed that, and we used then in 80s, 90s, we started using these composites in construction. So it's a kind of getting benefit from ideas from other disciplines and so on.
That's interesting. So I guess if we have any friends from any other courses, get in touch with them, because any good idea can come from anywhere. One more question is, what is the future of these composites?
Actually, these composites are used a lot in your, if you are looking at this session with your laptop, most of processor, the chips inside your laptops are made of glass fiber composites. And also, if you have Dell laptops, most of Dell laptops these days, the case is made of carbon fiber. And when you get into an airplane, for example, Boeing 787, now more than 80% of that plane is made of carbon fiber. So there are a lot of application of these fibers all around the world. In turbine blades, obviously, they are mostly made of FRP materials. They are mostly made of glass fiber composites.
Interesting.
If you are specifically asking about construction, for construction, we use these materials as rebar. Instead of having a steel rebar, we can have glass rebar or carbon rebar, mostly glass rebar and a fiberglass rebar. They are very durable against harsh environment. They are mainly used in concrete and replace the steel rebar in concrete in marine environment. Or even for pedestrian bridges or different types of bridges, they use these composite materials.
Okay. Great. We're running out of questions now, but what motivated you to pursue this field of research?
I guess since 4 years ago, I decided to change my direction of my research to sustainability. And at the moment, most of my research and work, and most of the work that my PhD students doing, they are related directly to sustainable materials or structures. So it is the need of the environment, the need of community, and this global warming is affecting everyone, obviously, and any kind of work that we can do to stop it or somehow reduce it, and avoiding contributing to this global warming and CO2 emission, that would be something interesting and would be valuable to pursue. So that's how I mainly try to focus on, and which I think is the need of the society at the moment.
All right. So I think these have been asked before, so I think we'll just ask the last question here. What opportunities do you have for theses? I think this is for all of our fourth year civil engineering students here.
Yeah, no, that's good, actually. That's a very good question. I have projects on these topics, or if you are interested on sustainable materials or sustainable structures, these kind of topics, just drop me an email. I'm interested to hear about that. Also, if you are interested to do PhD, I have PhD positions for these projects. Other projects that I also work on is on structural health monitoring using fiber optics, and also 3D printing of composites. So if you are interested on these, please reach out. So drop me an email. I'm more than happy to have a discussion with you.
Awesome. So that's I think that will wrap it up for today. Thank you again, Dr. Ali, for coming to present. If I could trouble everyone to turn on their face camera so that we could take a picture of everyone, that would be very great. I hope I can do this correctly. All right. Looking great, everyone. Hope we're having a good time this Wednesday evening. All right, great. We do have 2 more announcements just before we end. I guess 3. The iBuilding participation form is still up, so if anyone wants to sign up for that, that's still there. And next week, Wednesday, if you want more PEP hours, there'll be the next industry talk. And the day after that, September 8th, will be the comfort food Are You Okay event. I'll be the one hosting that. So if you want to come and chat or just enjoy some nice food, I'll be there in that event. If you want your PEP hours or anything like that, or if it's anything wrong, just contact the SUCE team and then we'll try and get it sorted out as quickly as possible. But if you attended this entire meeting and presentation, there should be no problem. So with that, thank you everyone for coming. Hopefully we'll see you in the next academic panel or the industry talk and any more future SUCE events. Thank you.